Welcome to the Explainer. If you've ever wondered how massive machines transfer crazy amounts of power from one spinning shaft to another without just flying apart under all that stress, well, you are in exactly the right place. Today, we're decoding the hidden mechanics of our everyday world using this incredibly fascinating visual guide to mechanical couplings.
Here is our roadmap for today's Explainer. First, we'll cover the anatomy of a connection, followed by simple and solid designs and the power of bolts. Then we'll move on to flexible connections, complex mechanisms, and finally, wrap things up with the perfect fit.
Let's kick things off with Section 1, Anatomy of a Connection, Decoding the Basics. So, let's establish exactly what foundational mechanism we're analyzing here. Basically, a coupling is a central junction where two ends meet. It's a really vital mechanical device designed to join components together so they can efficiently transmit power. You'll see this function playing out through all sorts of varied cylindrical junctions, with each one specifically engineered to bridge the gap between two moving parts. Just take a look at the sheer scale and variety of this full visual taxonomy. Each of these 15 distinct designs represents a very specific engineering choice made to solve a unique physical problem. Honestly, there is just no one-size-fits-all when it comes to mechanical engineering, and this incredible spread absolutely proves it by showing us 15 completely different ways to connect two shafts. Moving right along to Section 2, Simple and Solid Designs, the Foundation. We're going to begin our taxonomy with the designs that appear as single, solid pieces. Keep your eyes peeled for these simpler forms. They rely heavily on smooth, continuous cylindrical shapes. Those are really the fundamental building blocks of a connection, where the main goal is just straightforward, unyielding alignment. Notice the sturdy, simple, rigid coupling. Look at how blocky and unified it appears. Right next to it, the sleeve coupling introduces our very first vital annotation, tiny holes explicitly labeled with the word set screws. And those set screws, they tighten down to secure that smooth metal sleeve directly onto the shafts. Which brings us to Section 3, the power of bolts applying pressure. As we escalate the complexity, we transition to designs that are clearly engineered to be held together by heavy external hardware. Try to spot these three specific fastened couplings: the flange coupling, the split muff coupling, and the flexible coupling. These stand out instantly, don't they? They step completely away from those smooth, minimalist cylinders and instead rely heavily on visible bolts to create some intense clamping pressure. Look really closely at that flange coupling. The artist actually labeled the word bolts in 3 separate places around its rim, just to make absolutely sure we understand how critical they are to this design. Now compare that to the split muff coupling right beside it. This component is literally sliced horizontally down its entire length, and it features 4 massive, highly visible bolt recesses designed to clamp the two halves together. Now, this intense visual contrast naturally begs a pretty big question. Why in the world does the split muff require so many heavy bolts to grip the connection, while the sleeve coupling we looked at just a moment ago only needs those tiny set screws? Well, the answer lies in the visual evidence. All those thick bolts strongly suggest a serious need for immense, secure clamping pressure. In environments that are generating massive rotational force, a simple little set screw just wouldn't survive the torque. That heavy, visible hardware is essentially an engineer's way of ensuring absolute structural security when the pressure is at its absolute highest. All right, on to Section 4, Flexible Connections, Designing for Movement. So, we know some connections need to be completely rigid, right? But what happens when mechanisms actually require bending? Or maybe they just don't align perfectly? To answer that, we have to contrast the solid, blocky designs we just saw with ones that feature clear visual cues of movement. We're talking about things like hinges, interlocking gaps, or flexible ridges that can adapt to varying angles without snapping. This brilliantly illustrates articulation in action. Notice the sharply angled design of the clearly labeled universal joint, which allows the shaft to dramatically change direction. Then, check out the jaw coupling with its distinct interlocking teeth. It features just enough of a gap to accommodate tiny shifts. Finally, glance at the bellows coupling, boasting these awesome accordion-like ridges designed to stretch, compress, and bend. These visuals clearly tell us that flexibility is just as crucial as rigidity in the mechanical world. Now for Section 5, Complex Mechanisms, the climax of design. Let's see how all this builds to the climax of our visual tour,
In this final grouping, we aren't just looking at solid metal cylinders anymore. Oh no, we're seeing a massive leap in engineering. We've got internal nested geared structures, multi-layered flanged plates held together by highly specific hardware, dramatic cutaways showing turbine-like fins, and highly precise cross-sectional diagrams.
Just observe the sheer density of detail here. Look at the highly intricate nested gears of the constant speed coupling. I mean, it is literally a labyrinth of metal. Right next to it is the diaphragm coupling, showcasing multi-layered plates with explicit diaphragm labels pointing to the thin, flexible membranes sandwiched inside. And then, taking it to a whole other level, we have the stunning cutaway of the Fluidex coupling, peeling back the exterior to reveal a turbine-like interior. That tells us fluid is doing the heavy lifting there. Finally, check out the precise cross-sectional diagram. It features a handwritten label that appears to read Croxable Sechuan, clearly illustrating a cross-section. This specific drawing shows us exactly how these complex flanged parts mate together internally, layer by layer. It's like getting an X-ray view right into the mechanical architecture. Which leads us to our final section, Section 6, the perfect fit, mechanical evolution. From smooth sleeves to finned turbines, this single illustration has taken us on an absolute masterclass of mechanical evolution. By carefully studying it today, we've essentially learned how to read engineering designs. By simply observing the shapes, the specific types of fasteners, and the structural complexities across these 15 fascinating parts, we can actually decode the physical story behind them. We can see exactly why a designer chose a heavy bolt over a set screw or a flexible bellow over a rigid block. I'll leave you with this final thought. Practically everything moving around you right now relies on these hidden connections to function safely. With so many highly specialized ways to connect components, which coupling is turning the wheels of your world right now? Keep your eyes open, and you just might spot one.